In Module 1, we looked at a pedestrian crossing example to introduce some basic concepts of probability, particularly conditional probability, and how we handle that. Here we're going to generalize some of those concepts of the probability mass function and cumulative distribution function that we introduced in that example, along the way to getting to two extremely important mathematical concepts of the mean and of the variance, and mathematically how we're going to treat those. We're going to see those two concepts return to us throughout the entire course here that we'll see over and over and over. And we'll introduce a variety of different kinds of concepts along the way here. So let's go back to that pedestrian crossing example where we were looking at the distribution of the possible gaps between vehicles, and we chose to discretize those gaps into 5 different possible outcomes: 3, 6, 9, 12, and 15. And so those properties that we're going to be talking about here in terms of the context of discrete random variables, where only specific outcomes of the random variable are possible, are going to have an analogy that will be sometimes seamless and look no different than for the continuous domain, as what we're doing here. And in other cases, it will look a little bit different, and we'll point those out as we go along. Right, so the relative frequencies of these possible discrete outcomes were in that 1 to 2 to 3 to 2 to 1 ratio. And last time in that example, we had looked at this probability mass function of this interarrival time, or gap, and we had come up with the following. And we hadn't quite expressed it in this particular set of mathematical notation, but this PMF is oftentimes given the lowercase symbol p for the symbol of the PMF, and then subscript capital T, we talked about that, and then a possible value, or the argument, being t sub I. The little I indicating again that this is a discrete random variable. This is our PMF. Some people use a lowercase f for this. I don't like to do that because that tends to represent something else. But this is our probability distribution. And we had a 1/9 chance that Ti, our gap, any arbitrarily selected gap, was going to be equal to 3 seconds. Or it also turns out that it was also, note the relative ratios here, that was true for the 15-second gap as well. And then 2/9 for Ti equal to 6 or 12 seconds, and then 3/9 for the probability mass for Ti equal to 9 seconds. Now, we had this last time, we just wrote it in terms of a tabular format rather than in this more mathematically pristine kind of example. Now, a couple of things to note here and some basic properties. That this symbol here, again, directly means that is the probability that our random variable takes on a specific value. Right, so, for example, Pt of Ti equaling 3 was equal to 1/9. And so that's what one of the properties here. Another one is that note that each and every one of the probabilities is greater than or equal to 0, and that has to be true. There's no such thing as a negative probability here. Okay? And then finally note that if we wanted the probability that t was less than or equal to t sub I, then I'm going to introduce a dummy variable here, but we would just simply sum up then all those probabilities of Ti being less than or equal to Ti star. Now, you'll find in some textbooks they'll write these in a slightly different kind of way. They'll emphasize a slightly different version of that. But those are 3 basic identities associated with this. And note then also here that this lowercase pt of Ti, that functional symbol for the probability mass function, then this last one is our CDF, or in terms of symbols, we'll give that a capital F sub t of ti. That's our cumulative distribution function. And some people place a lot of emphasis on the meaning of the symbol itself, whether it's, in other words, it's case sensitive. So uppercase is cumulative distribution function, a lowercase means probability mass function for a little p. If this were a continuous random variable, where we'll let t take on 3.12845 or whatever, real numbers, then this would be a lowercase f for the probability mass function. That's why there's that distinction that is out there.